All right, today we're jumping into one of the most famous, most mind-bending puzzles in all of physics. Seriously, get ready to question everything you think you know about time.
It all boils down to this seemingly simple question. Imagine you have two identical twins. One of them gets on a super fast rocket, flies to a distant star, and then comes back home. When they finally reunite, is one of them actually younger than the other? The answer? A resounding yes. And how that's possible? Well, that's where things get really weird.
Okay, so this is the heart of the so-called paradox. From Terrence's point of view on Earth, his sister Stella is zipping through space, so her clock should tick slower. Simple enough. But wait, from Stella's rocket, Earth is the one moving away, so Terrence's clock should be the slow one. See the problem? They can't both be younger when they meet up. So what gives?
So to untangle this, let's set the stage. We've got our two twins, Stella, she's our astronaut, and Terrence, he's the one staying home on Earth. Stella's mission is pretty straightforward. Blast off, travel near the speed of light, turn around, and come home. That's the whole setup.
Now, here's the most important thing to get straight right away. This isn't a flaw in Einstein's physics. Not at all. In fact, it's one of the best ways to prove his theories are right. The paradox is really just a flaw in our everyday human intuition. Our brains didn't evolve to handle the weirdness of space-time, but today, we're going to give them an upgrade.
All right, so how do we crack this thing? Well, the first and kind of simplest answer boils down to one key idea: breaking the symmetry. Because even though their journeys might look like mirror images of each other, they are absolutely not the same.
And to see that difference, we have to talk about something called an inertial frame. It's just a fancy term for moving smoothly. You know, constant speed, constant direction, no acceleration. Now Terrence, back on Earth, he chills in one single inertial frame the entire time. But Stella? No way. She has to be in one frame on the way out and then a completely different one on her way back.
And making that switch, well, that requires acceleration. She has to slam on the brakes, turn the ship around, and floor it again. She would literally feel those G-forces pinning her to her seat. Terrence feels nothing. That experience, that acceleration is absolute. It's a real physical event that breaks the symmetry completely. It happened to her, not to him.
But, you know, saying it's the acceleration feels a little like a cop-out, right? It's the what, but it's not really the deep why. To get to the real heart of it, we have to stop thinking about space and time as two separate things. We need to look at the very geometry of the universe.
And you know who gave us the key? Over a century ago, a mathematician named Hermann Minkowski. He had this incredible insight, beautifully captured in this quote. He realized that space and time are fundamentally interwoven into a single four-dimensional fabric. He called it space-time. And it's not just a cool concept, it is the stage where all of reality plays out.
So, to help us picture this, we use an idea called a world line. Just think of it as the unique path that any object, you, me, a planet, a spaceship, takes through this 4D space-time. It's basically a map of your entire existence through space and time. Now, Terrence's world line is super simple. Since he's just staying put on Earth, he's not really moving through space. His path is just a straight line, going directly up through the time dimension. It is the most direct route he could possibly take, between the moment Stella leaves and the moment she returns.
Stella's path, on the other hand, is totally different. She travels out through space, and then she travels back. So her world line isn't a straight line at all. It's a triangle. Here's the key. They both start at the same point in space-time, and they end at the same point in space-time. But they took two wildly different routes to get there.
And this is where the geometry of space-time just completely blows your mind. In our normal, everyday world, the shortest distance between 2 points is a straight line, right? Well, in space-time, it's the exact opposite. The straightest path, Terrence's path, is the path of the longest elapsed time. By taking that detour through space, Stella literally shortens her path through time.
Okay, so that's the geometry. But let's put some actual numbers on this to see how it all shakes out. Let's say Stella travels to a star 4 light-years away, going at 80% the speed of light. Now, from Earth's perspective, the round trip takes exactly 10 years. But for Stella, inside her ship, only 6 years will have passed. The crazy part is that Stella's own math will confirm this.
So how does Stella's math work out? Where's the missing time from her point of view? It all comes from this one wild moment, her turnaround. That one act of acceleration doesn't just change her direction. It dramatically shifts her entire frame of reference of what is happening now back on Earth.
In our example, that single event causes 6.4 years of Terence's life to instantly flash forward in her calculations. It's a concept called the relativity of simultaneity, and it's the key. Because think about it, during her trip out and her trip back, from her cockpit it looks like Terence is the one aging slower. She'd calculate he's only aged about 3.6 years. So she's sitting there thinking, wait a minute, my clock says 6 years have passed, but his clock only says 3.6, but everyone on Earth says he's aged 10 years. Where did that missing 6.4 years of his life go?
And the answer is, it didn't go anywhere. That massive simultaneity shift during her turnaround, that 6.4 years, it just zaps into her calculations all at once. So when she adds it all up, the 1.8 years she saw him age on the way out, the 1.8 on the way back, plus that massive 6.4-year jump from the turnaround, it all adds up perfectly. 10 years.
So you see, when you do all the math, both twins come to the exact same conclusion. Terence has aged 10 years, Stella has aged 6. Their numbers match, their observations match, the physics works perfectly from every point of view. There is no paradox.
Now, I know what you might be thinking. This is all fun, mind-bending, sci-fi stuff, right? A thought experiment. But it's not. Time dilation is a very real, measurable phenomenon that has a direct impact on our world and the technology we use every single day.
For starters, take muons. These are tiny, unstable particles created way up in our atmosphere. They should decay long before they reach the ground, but they don't. Why? Because they're moving so fast, their internal clocks slow down, giving them enough time to make the trip. Or how about the Hafele-Keating experiment back in 1971? They literally put atomic clocks on airplanes, flew them around the world, and measured the tiny time difference that relativity predicted. And maybe the most important example? The GPS in your phone only works because we constantly account for this stuff.
See, GPS satellites have to deal with two competing effects from relativity. First, because they're moving so incredibly fast, their clocks actually slow down by about 7 microseconds every day. That's special relativity. But because they're farther away from Earth's gravity, their clocks actually speed up by almost 46 microseconds a day. That's general relativity.
So when you put those two effects together, you get a net result. Every single day, a GPS satellite clock gets ahead of a clock on Earth by about 38.6 microseconds. Now that sounds tiny, right? But for a system that relies on nanosecond accuracy, it's a catastrophe waiting to happen.
And here's what that catastrophe would look like. If the engineers who built the GPS system just ignored relativity, the positioning errors would pile up at a rate of more than 11 kilometers, that's about 7 miles, every single day. Your phone's map would be completely useless within hours. So yeah, relativity isn't just some abstract theory. It's the reason your Uber finds you.
And that really brings us back to the core mind-bending idea of it all. If the amount of time that passes for you depends on the specific path you take through space-time, then what does a word like now even mean? The twin paradox teaches us that there is no universal clock ticking for everyone. Time is personal. And that is a truly profound thought to end on.